All right. Well, good morning, everybody. This is Mr. Rich. Welcome to my live stream this morning.
All right. Well, good morning.
And what we want to do is do a few problems here on AP Precalc. So I'm doing a few live sessions here in the middle of the day. Probably not going to get too many viewers, but just doing this kind of as a trial run because I am going to be doing a live stream this Sunday at 7 p.m. and that's going to be for a full hour, and we'll do an AP Precalc exam review, and I'll be working some free response questions that you might expect to see something similar to on your AP exam in May. All right, so let's get to it. All right, so the first problem here that I want to work is an inequality. This is a polynomial inequality. We need to find all the values of x for which this is going to be true. So what we want to do is we're going to go ahead and factor this, and we'll factor out a common factor first of x. All right, and so we've got that. Now this leaves us a quadratic that can be pretty easily factored. And this will be x minus 3 times x minus 3. So what this does is this tells us there are two x values for which we have zeros on this polynomial. And what I'm going to do is I'm going to show you several ways to approach this. One of the zeros, let's write down the zeros here. So the zeros are going to be at x equals 0 and x equals 3. So one of the ways that you can analyze this is kind of I'm just looking at my x-axis, and those are points there where the polynomial is going to be touching the x-axis. One thing we know about this is a third-degree polynomial with a positive leading coefficient. So we know that if we were to take a look at this, the end behaviors are going to be up to the right and down to the left. Again, because we have an odd degree and we have a positive leading coefficient, I know that's what the end behaviors are. Furthermore, I know that the 0 x equals 3 has a multiplicity of 2. And so what's going to happen is the function is going to bounce off of the x-axis when it gets to that 0 at 3. So the general behavior of this function is going to come like this. We're going to bounce off of this 0. And at some point here in between 0 and 3, we're going to have to turn. And when we get to x equals 0, the polynomial is going to pass through the function. And so here I can actually, at this point, answer the question, because this says, when will this polynomial be less than or equal to 0? Well, I have two parts to that answer. It is going to be less than 0, meaning below the x-axis, out here to the left of 0. So one of my solutions, if we write down our solutions here, is going to be from negative infinity up to and including 0. But notice the equation is going to be true out here just at that value of 3. So I'm going to include that. That's not an interval, right? That's just a particular point. And in AP, you could probably just say comma, and then in set notation, put the number 3 like that. Or you could put a union symbol between them. But those are all of the x values for which this inequality is going to be true. Now, one other way to approach this, if you weren't aware of the end behaviors of the function, and you could come to that conclusion, one of the things that we do is this. We are going to pick some test points in the three intervals that are created by these two zeros. I'm going to pick x equals -1 to the left of 0. I'll use x equals 1 to be between 0 and 3, and then I'll use 4. what I'm going to do is I'm going to put these test points into the factored form of the polynomial. And all I really want to know is whether the value that's returned by the polynomial is a positive or a negative, right? So I'm looking for values that are less than or equal to 0. So when x is a -1, that x right there would be a negative. When I plug the -1 into the next factor, that's also a negative. And of course, that's also going to be a negative. So this is going to give me a negative value. So I know to the left of 0, the function does go below the x-axis, and it would be a region for which this inequality is true. Now, when x is equal to a +1, it's going to be a positive from that factor, and it would be then 2 negatives, which makes a positive. So all of these values between 0 and 3 are going to be above the x-axis, in which case they would not make that inequality true, less than 0. Over here, when it's 4, it's a positive times a positive times a positive, which also gives me a positive. So this tells me then that it is from this analysis that all of these values of x back this way are going to be solutions. None of these between 0 and 3 or greater than 3, but yet I know that 3 has to be included because of the fact that it was or equal to 0. Okay, so that is a polynomial inequality. There are two more, at least, that I wanted to work this morning, and let me pull the next one up. The next one is a trig. I realize I think I had advertised this as being trigonometry equations. That obviously was not trigonometry, but here is the trig equation that I wanted to take a look at. And you might find this one to be somewhat challenging. That's why I picked it. And it looks like this. All right, so now the reason why this would be challenging, right, is if we're trying to solve for x, I have a sine and a cosine. And I want to try to replace, try to get myself down to one trig function in my equation so I could solve for x. Now, yesterday I worked a problem where it turned out where it worked out where we could maybe divide everything by sine x. I don't think this is going to work. It's possible it does, but it's not the easiest way. This would leave us root 3 minus cotangent of x is equal to 2 cosecant of x, right? I move that sine x up into the numerator and it'll become a cosecant x. Now, that's maybe not the handiest way to do this, unless perhaps I squared both sides at that point and could use a Pythagorean identity. I'm not going to do that. It's something that you might want to try and see if you squared this. I'll go down that path maybe just a little bit and see what happens. I don't think that's going to work. But if I square this binomial, I'm going to get 3 minus 2 root 3 cotangent x, and then I would have plus cotangent squared x. On the right-hand side, what that's going to give me when I square this, it's going to give me 4 cosecant squared x. Now here, I do have a cosecant squared now and a cotangent squared, which might open the door for a possible Pythagorean identity, but I don't think so because of the coefficient 4. All right, so I'm going to scrap this idea and go to another method that we could use. In fact, we will, let's just get rid of all this and get back to our original problem. Now, one of the things that I notice here is that if I were to divide by 2 all the way through, this becomes this. And this would be a minus 1/2 cosine x when I divide that by 2. And that gives me a 1 on the right-hand side. Now, this looks a little bit familiar here. because I noticed this root 3 over 2 and negative 1/2. Now, if I consider the unit circle, that looks like a particular point, right, on the unit circle. So one of the things that I could do is I could think about doing a sum and difference identity, making this into a sum and difference identity by realizing that if I pick the right um, angle, I could get this root 3 over 2 and negative 1/2 so that this was my, and I could do it either one, actually. I could make this cosine and this sine. So let's just pick, let's pick this point over here on our unit circle. That's going to be 5 pi over 6. Now, what's that going to give me as a point? That point at 5 pi over 6 is going to be a negative root 3 over 2, comma 1/2. That's our unit circle point at 5 pi over 6. So that means that I could replace 1/2 with sine of 5 pi over 6. Okay. And I could replace root 3 over 2. That would make it into a negative. So, but I could replace that then with a negative cosine x. So in other words, I'm going to replace this with negative cosine of 5 pi over 6. Now, but I will tell you that really what I want to do is I want to make this one a positive. So I think what we will do is we can, let's just use pi over 3. Let's come over to this side of the unit circle. So if we come over here to not pi over 3, but pi over 6, what that point is there is root 3 over 2, comma 1/2. I think you would agree with me there. What that allows me to do then is replace the root 3 over 2 with cosine of pi over 6. So I'm going to write this as cosine pi over 6 times sine x. This 1/2 I'm going to replace with sine of pi over 6 times cosine of x equals 1. And this takes me to a sum, actually a difference of sine, of a difference of two sine angles. So remember the identity that you need for the sum and difference for sine. We said sine of angle A plus or minus angle B would be equal to sine of A cosine of B plus or minus, we keep the same sign in between these two terms, and then this would be sine of B cosine of A. And that is the situation that we have here. And what we have is this is going to be the, for us, this would be our A, and this would be our B. So we would say sine x times cosine pi over 6 would be A and B. And then you can see that they switch over here. Okay, and then this becomes the, that becomes the B, and that becomes the A right there. So I could rewrite this then like this using this formula. This would be the sine of x plus pi over 6, and that's equal to 1. So I'm using that identity right here, and I'm using the identity in reverse. I'm taking this and rewriting it like this. Now there's a minus, so we do need to keep that sign right here. That's going to be a minus right there. Okay, and let's just check and make sure that that's right, right? This would be sine x cosine pi over 6 minus sine pi over 6 cosine x. And so therefore, what we can do now is say, okay, let's consider when is sine of an angle equal to 1. Well, there's only one point in the unit circle where that's going to occur, and that's going to be at pi over 2. So therefore, this angle, x minus pi over 6, has to be equal to pi over 2. And then that allows me to solve for x. And then what I'm going to do is I'm going to add pi over 6 on both sides. And that's going to look like this. X is equal to pi over 2 plus pi over 6. And don't forget, we are going to add on here, if we're finding every solution, 2 pi times k, where k is an integer. So we're going to keep that 2 pi k here, but add the pi over 6, and then we can add that to be 3 pi over 6 plus pi over 6, 4 pi over 6, or 2 pi over 3 plus 2 pi k. And there's our solution. So a little bit of a trickier one, and that's what it is. That's what we had to do there. Divide by 2, and then replace those with one of the with cosine and sine from our unit circle. That would be at those 2 points. Now, I am going to show you how to check work using Desmos, right? As you're learning to do problems like this, what I would recommend doing is graphing things in Desmos. So I'm going to try that here. And let's pull this over just a bit. So here's what I'm going to do. I'm going to make sure that my calculator is in radians mode, and it is. So I'm going to graph the left-hand side of this equation, which is the square root of 3 times sine x and minus cosine x, right? So that was the equation there. We don't want an s there. There we go. So there we go. And then I'm going to graph the right-hand side of the equation, and the right-hand side of the equation was the number 2 over here. And so I will then graph y equals 2, which is the right-hand side over here. And we're looking at this at the intersection point here between these two graphs. And if we zoom in here and look at the intersection point, it's at 2.0944. That's what that is. Now, let's calculate 2 pi over 3 as a decimal. And you can see 2 pi over 3 as a decimal is 2.049. So when you're graphing functions and you look at the intersection point, the x coordinate, when you've graphed the left and right hand side, that x coordinate is going to be your solution to the equation. So we kind of are confirming it. And you can see every period after that, the next solution is going to occur here. And that's going to be 2 pi over 3 plus 2 pi. And then over here, it would be 2 pi over 3 plus 4 pi. So every 2 pi radians, we're going to get another solution to that. All right, I have one more that I'm going to work in this live stream, and it also is going to be a trig equation. So let's move this back. Okay, and then we'll go down here and we'll tackle the next one. And here's what it is. This one's going to be 2 cosine squared x minus 7 cosine x plus 3 equals 0. So we recognize these kinds of equations as quadratic type equations, right? I have a cosine squared, then a cosine to the 1 power, and then just a constant. So we're going to try to factor this into the product of two binomials. And the 2 cosine squared x can be split up in only one way, and that would be 2 cosine x times cosine x. And I know that these other terms that I'm looking for both have to be negative, because I've got a positive 3 but a negative 7. And by just some trial and error, if I put the -3 and the -1, which would give me my +3 constant term, that's going to work. Because remember, when you're checking whether you have the right numbers put in for your binomials, the inner term, right, this middle term of your quadratic equation is going to be the combination of the outer and inner products. All I'm looking at here is the outer products being -6 cosine x, the inner product being negative cosine x. And that combines to be -7 cosine x. So I know that I factored it correctly. Well, just any other time that we have 0 on the right side and we have our expression in factored form, we're going to solve it by setting each of those factors equal to 0. And we'll do just that. Now we're going to isolate the cosine x. Here we got cosine x is equal to a +1/2. This one is going to be cosine x equals 3. Now cosine and sine both are never going to reach a value of 3 because their outputs are from -1 to 1. So this yields no solutions for x. All right, but that's okay. It just means this factor will not give us any solution to the overall equation, but this one is going to, because I know that cosine will be 1/2 at two different angles within 0 to 2 pi. One of those is going to be at 2 pi over 3, or excuse me, pi over 3 is the first one. And then the second one is going to be down in the fourth quadrant at 5 pi over 3. Right now, I want to include all solutions. And so what I would do is I would tack on here. I would have to go a whole nother period, 2 pi k right there. And then this one also plus 2 pi k, where k is an integer. That gives me all of the solutions. When you put an integer in for k, both of those expressions are going to give you solutions to the original equation. Okay, that's it. So just be on the lookout for these where you really don't have a solution to one of your factors when you set it equal to 0. And again, that's because the maximum value of cosine is 1. Its minimum value is -1. It never goes above 1 or below -1. So there's no way that you could solve that equation. All right, everybody, I hope that was helpful. And don't forget, again, this Sunday night, if you are watching this, Sunday night, April the 13th is when I'm doing my first AP Precalc exam review. I'm going to be focusing in on free response questions that you might see on your AP exam in May. Have a great day, everybody. Hopefully, I'll see some of you on Sunday.